In this particular video, I want to talk about spread spectrum technology. Now, this is very highly relevant, especially to Wi-Fi, but also to other wireless communications as well. Now, there are several reasons for this. Before we dive into those reasons, I want to look into a history quickly. Like, how did this all start? So this was first developed, during World War II, initially for military use, so that they could secure the communication so that nobody can intercept that communication and nobody could jam that signal. Now, once it was created by the military, then it got passed down to the commercial applications, specifically in wireless communication like Wi-Fi. Now, if you look at the types of spread spectrum, there are two types. The first being the frequency hop spread spectrum. Now, the signal hops between frequency to frequency within a particular bandwidth at a very predictable rate that is both known to the transmitter and receiver. The second one that we also use in Wi-Fi is the direct sequence spread spectrum, DSSS. A digital signal is, think of that as multiplied at a higher rate sequence, and it is spread across a wide frequency so that it is, kind of protected from any sort of interference. So this is the main reason why it is preferred for Wi-Fi. Now, spread spectrum techniques are effective in minimizing the impact of multipath interference, which is very common in Wi-Fi, where the signal reflects off different surfaces and you can get multiple signal at the source, and then it could cancel each other in certain cases, right? So when using spread spectrum facilitates compatibility as well, because you have different bodies that are, regulating. You could be in different countries. So if I have a technology that is well developed and accepted by everywhere or all the parts of the world, then I can have that particular communication anywhere I want. So inside I have a device that is supporting a certain standard. Now it doesn't matter if I go to which part of the world, as long as it's supported by everybody, then it makes it that much easier. Then also another thing is the narrowband, right? So the narrowband, what is narrowband? See, narrowband is when you're transmitting the digital over a very narrow band of frequency, right? Typically, this will be true in case of an AM. And the third thing I want to talk about is also going to be OFDM. This is a type of a digital transmission. It's a key method used in wireless networks, especially on the later standards. If you look at it, it's where you're splitting the high data stream into like slower streams by taking it into smaller subcarriers, and where all these signals are orthogonal to each other, which we'll talk what does that mean in this video. Before any further delay, let's get into the actual video and start looking into these technologies in a little more detail. So let's dive in. So let's start by looking at spread spectrum first. So the main thing to remember is that it's basically going to transmit a signal across a wide frequency band. By spreading, I'm making my signal much more reliable because it's spread all across a wide frequencies. It doesn't mean that somebody can jam my signal on a specific frequency now, so it makes it more reliable. That's the main purpose of the spread spectrum here. As it is spread, inherently it is resistant to interference from other signals like electronic noise, which is crucial in especially crowded frequency environments. Spreading the signal over wide bandwidth, it becomes harder for the eavesdropper to intercept or disrupt the communication effectively, making it more secure as well. Talk about multiple access capabilities. We need to understand the concept of CDMA, which is code division multiple access, which really means I'm giving the spectrum technology to allow multiple users to share the same frequency band simultaneously without significant interference. In specific Wi-Fi, we use CDMA CA. CA stands for collision avoidance, which we'll discuss in further videos what avoidance really means. Technology is also able to mitigate multiple multipath effects. Now, basically what happens is when multiple signals come through, they are going to be interfering because signals are arriving at the receiver at different times due to reflecting off various objects. Flexible and scalable, as it can easily accommodate more users to improve quality of service by adjusting the spreading codes or bandwidth. And this is useful, definitely, especially in rapid growing or changing environments. A few more points on spread spectrum, but the main thing I want to take away here is it uses more bandwidth than is necessary, but again, that's important as well. And some things that you see here, the points, we've already discussed them, so I'll go forward. Now this is comparing narrowband and spread spectrum. Obviously, if you look at the power of the narrowband, it's much higher because it has that power peak. Spread spectrum is low, but frequency narrow is very specific, whereas spread spectrum is a wide frequency range. As I mentioned before, narrowband technology refers to using a very narrow range of frequency or a single frequency to transmit data. It is characterized by a limited bandwidth and often associated with radio systems like AM radio, right? Like in case of AM, it needs to reach a far audience. It's typically transmitted at a much higher power than the spread spectrum signal. Typically, FCC or any other local regulatory bodies would require narrowband transmitter to be licensed like an AM or an FM station. If I'm running an AM or FM station, I cannot be transmitting on any other frequency rather than the one that has been given or licensed to me. Here are a few of the features of narrowband. One thing I want to point out is look at the penetration part. That's what's important. That's what drives the AM use case there, right? And it also used by walkie-talkies, emergency radio services. Now here we look at some of the benefits like the reduced interference, the cost effectiveness, and the long distance communication. Now the application would depend on the actual limitations or options that the technology brings, right? So for example, it has a bandwidth limitation, not suitable for high rate applications such as video streaming or large file transfer. You have to be careful with their regulatory compliance, much adhere to a certain frequency range, cannot interfere with other narrowband transmissions like other radio stations. If I'm on a radio station, those are the kind of application restrictions I have. So applications would be IoT, control channels, obviously in cellular where I'm using very specific frequencies for communication. And on the screen, you see three major types of spread spectrum. OFDM not really is part of the spread spectrum, but it kind of is the same technology that helps widespread the frequency. Narrowband has three problems: interference, jamming, and interception. Frequency hop spread spectrum uses a spread spectrum technique, which the signal is generated with a particular bandwidth and is deliberately spread between that or within that frequency band. But if you move forward and look into more depth for frequency hop spread spectrum, it has been deprecated and completely removed from the current 802.11 2020 standard. Still important to understand the basics behind the FHSS, as other technologies such as Bluetooth is using it today. Number of hops, the dwell time, and the hopping sequence is very different from Bluetooth versus 802.11 FHSS again. And why should I care is because it is important to understand that the Bluetooth does operate on the same 2.4 GHz band, which is exactly same as our 802.11b, G, N, and AX devices. So they can very well overlap and interfere with each other. So how does even this work? So signal jumps between different predetermined frequencies with a wider band. Imagine yourself playing hopscotch when you were a kid, right? You jump from one square to another in a random order that only you and your friend know. Just like FHSS, outsiders can't predict your next move, making it harder for them to intercept your path, basically. Two things I need to understand with frequency hop spread spectrum is what's my sequence, how I jump, dwell time, how long do I stay there, hop time, how long do I stay and then jump. That's one of the things that I need to understand when I'm doing the frequency hop spread spectrum. So if you look at it carefully here, is dwell time is how long I'm staying there. And then hop sequences, jump time between those jumps. And then the actual sequence is how am I jumping. I'm going from, say, channel 1 to frequency 5 and so on. And this was basically used by the first standard when the standard came out, which is 802.11, the FHSS. After that, it has never actually been used. And it was used on 2.4 GHz band. That pretty much we saw the direct spread spectrum being used more often because it gave you more speed. So that was kind of more adopted than the frequency hop spread spectrum, and that's why it was dropped. Key principle behind the DSSS is use of a pseudo-random spreading code known as a spread sequence to spread the signal across the wider bandwidth. In case you see that there have been 11 chips that will be added, that's why we require the 22 megahertz. And the spreading or the chirping relies on the pseudo-random code, and this code is a sequence of binary zeros and ones basically, which randomly appear, but they're kind of deterministic, generated at both the transmitter and receiver. That's how the receiver knows the code sequence used by the transmitter at this point. I really want you to remember here is at 802.11b, which was able to provide higher data rates, which was due to the HRDSS that adds more complex complementary code keying where it gets utilized. So instead of 11, it uses 8 chips. This table with DSS, you get 1 and 2. With HRDSS, which we get 5.5 and 11. Now we're going to move into OFDM, which is the most used, I would say, and that's why most important, the orthogonal frequency division multiplexing. Now imagine highways with multiple cars. Each lane represents a subcarrier. Now cars, the data packets can travel down each lane, the subcarrier, without interfering with each other, which means they will be able to be very close to each other in different lanes, but they will not be bumping into each other. The lanes are well marked and separated by clear lane markings. So pretty much that's orthogonal. It's one of the most popular communication technologies used both in wired and wireless. Now, if it gets used from a wireless perspective, you see it in 802.11a and G, N, and even the newer technologies, which are the AC and the AX. Using multiple subcarriers, it can maximize the spectral efficiency. If I had that big highway and I was only putting one car on it, but now because I've divided that highway into smaller lanes, I can have multiple cars going at the same time. It can also help with multipath environments, and it can improve the spectrum sharing as well. 12 of the 64 subcarriers in a 20 MHz OFDM channel are used and served as guard bands. Guard bands are unused part of the radio spectrum between the radio bands. Again, if you look at this diagram carefully, we have some guard bands to make sure that we have some kind of markings, the lanes, and then you have the pilots, which are helping us to sync up with the actual transmitter. Syncing up happens because now we're able to reference those four and kind of see that where I am, and I can kind of fine tune into the transmitter as a receiver. 48 of the subcarriers are used to transmit the modulated data. So OFDM is more resistant to the negative effects of multipath than DSS and FHSS spectrum technologies. And if you look at the orthogonal, this is what it really means. If I look at the red signal, the other ones are actually zero at this point. And now if I go back and look at the blue signal, if I keep drawing all the way down, the other ones are zero at this point. So they're not really interfering. When one peaks, the other kind of go down. Now this is everything. Whatever we've spoken about, this covers everything. So if you go with this slide, pause the video here and look through each and every steps, you will see exactly everything that I mentioned on this very slide. I'm really hopeful that this gave you valuable information, especially around spectrum and other technologies we spoke about. Looking forward to see you on the next one. Bye for now.